So we're going to start by discussing the questions that were just given as a test for the first week. All right, so the first question is, the most relevant force in solid-state physics is the strong force, the gravitational force, the Coulomb force. Coulomb, right? We discussed it last time. Certainly not the strong force, and the gravitational force is so weak that it's essentially relevant in solid-state physics. Which one of the following lattices is not a Bravais lattice? The Honeycomb Lattice, the face-center cubic, FCC, or the simple cubic lattice? Honeycomb, right? All right. Please. So the Honeycomb Lattice is not a Bravais lattice. If you have any question, please let me know. Simple cubic is obviously Bravais lattice. Face-center cubic, I sort of told you that it's a Bravais lattice. We didn't really prove it. Now comes the more difficult questions. The third one. I'm glad that you come in exactly when we discuss the most difficult questions. 3, 4, and 5. So the first two were just to warm up a little bit. Okay. Consider a simple cubic lattice. So we're talking about the cubic lattice, simple cubic lattice, and place in its unit cell. So I'm going to draw it now. Okay, so we have a simple cubic lattice. Let me put the A is the side of the cube, all right? And I'm placing an additional point in addition to this one. I place it at position at the center of the basal face, that is at position A over 2, and 0, right? So we're placing this new point here, correct? Right? If this is Z, this is X, and this is Y, it's actually the same, right? Independent of the way you order the axis. So the question is, the new lattice, right? The new lattice that is formed by placing a point at the center of this face, is it a cubic lattice with a basis, which cannot be reduced to a Bravais lattice, a tetragonal Bravais lattice, a cubic Bravais lattice? Okay, now if you forget about the third axis, this is a problem that we already discussed last time, right? We took a square lattice, we placed an atom at the center of the square, you remember last time. We placed an atom at the center of the square. It's like seeing this from Z, along Z, right? It's like we're viewing that along Z. So, of course, this can be seen also as a lattice with a basis, right? A basis, a square lattice with two atoms with 2 points in the basis. But it can also be seen, as we discussed, as a Bravais lattice, a square Bravais lattice tilted by 45 degrees. Now, if we now interpret this picture based on this one, well, you now clearly see that here you could have done the same for the basal plane, right? So you could have identified a square Bravais lattice on the basal plane, right? So then what you are forming, the minimum lattice that you are forming, is a lattice made of this square basis and then the three-dimensional, the third dimension, which remains the same. Okay, so Now that you see this picture, you clearly understand that the correct answer was B, a tetragonal lattice, right? So this is a tetragonal lattice with the basis, with the third dimension square root 2 times the primitive vector in the plane. Okay? The first answer would be wrong because although it is a cubic lattice with the basis, it can be reduced to a Bravais lattice, as you have seen here. The third answer is wrong just because it's not cubic. It's not a cubic Bravais lattice any longer. Okay, so this was problem 3. Problem 4. Identify the sets of primitive vectors that generate a square lattice of side A. So we have a square lattice. Okay, let me redraw the original points here. So we have our simple choice of the primitive vectors like that. The square lattice has side A, so this is A. The length of this distance is A. And we have 3 possible choices of the primitive vectors. The first one is, let me use color chokes here, otherwise we're gonna. Choice 1 was A0, right? So that's A1. And for A2, 8A, A. So you have to move 8 times here. 1, 2, 3, 4, 5, 6, 7, 8. A. And I have to go here. So it's this vector here, A2. Second choice. First vector, the same. A1. Second vector, minus 2A. All right. Third choice. The first vector is A minus A. So I have to go A and minus. A2 is AA. Which one is correct? That is, which one of these 3 choices of primitive vectors generates the square lattice? So let me immediately find one that does not certainly generate the square lattice. And that's the red choice, right? The red choice, the 2 vectors are not linearly independent. So I'll never be able to generate the y direction here because they're all flat, they're on the plane. So whatever linear combination I take of A1 and A2, I will still lie on the plane. I'm not going to move outside the plane. So this is certainly wrong. So number 2, it's AAA. Well, in any case, it's number 2. The second choice is certainly not correct. What about the blue one? Is the blue one correct or not? What about this point? Are you able to generate this point with these 2 primitive vectors? You sum this with this, and you end up here. There's no way you can obtain this point. In fact, you see, this is a square lattice, but tilted, right? So these 2 vectors, A1 and A2, the blue ones, are generating a square lattice which is tilted, but it's bigger than the original one. You're missing the central points. The yellow one is okay. We've actually discussed several examples of these primitive vectors, right? We keep A1 fixed, and we have an A2 which can be everywhere on the second floor, as we said last time. All right, so only choice 1, only the first one was okay. The other two were not. Okay. Yes?
Then the other, if this is going to be a square lattice,
Which one?
the angle in between this one must be 90.
The yellow one? You're talking about the yellow, the blue, or the red one?
The yellow one.
The yellow one, okay. So you're arguing that the two primitive vectors, the yellow primitive vectors, there's no 90 degrees between the two primitive vectors, okay? We discussed it in class last time, one of the first times. We said that the choice of primitive vectors is not unique for a lattice. And we gave actually the square lattice as an example. There is the obvious choice, the white one, which was actually not among the possibilities, the obvious one, that is having the two vectors like this. But then we can choose in principle A2 to be any vector if we keep A1 fixed, that is the vector connecting these 2 points fixed. For A2, we can choose any vector that starts from here and ends up anywhere along the points of the second floor, right? Because by definition, the primitive vectors, you must be able to generate the whole lattice with the primitive vectors. That's the only condition you ask to the primitive vectors. You're not asking anything else. You must be able to generate all and only the vectors of your Bravais lattice. So here you can go everywhere using the yellow choice of the primitive vectors. You can go, for example, here. You just need to take A2 to go to the second floor, and then come back 8 times using A1 minus 8 times A1, and you'll get here. So you'll be able to generate all points of the square lattice by using the yellow choice of the primitive vectors. Now, as we discussed, there is an infinitely many possible choices of primitive vectors. Only a few, or perhaps even one, is more natural than the other ones. For the square lattice, I agree with you that the choice of the two primitive vectors being at 90 degrees, the white one, is the more natural one, the most natural one among all the possible choices. But it's not unique. There may be others. This yellow one, there's nothing wrong with that. You can generate the square lattice by linear combinations of integer times A1 and A2, A1 and A2 being the yellow vectors there. Nothing wrong with that statement. Okay? While you cannot generate all the points in the square lattice using the blue one, because this point will never be there in your you'll never be able to write this point as a linear combination with integers of A1 and A2. The red one is more obvious because they are aligned, and so therefore they are not linear independent. So you won't be able to generate the lattice outside this line here by linear combinations of integer times your primitive vectors. Okay? Okay. So now the fifth question. The fifth question was, what is the area of the unit cell of a triangular lattice? So let me draw a triangular lattice. I need to draw also a unit cell, and I can do it in several ways, right? We discussed it last time. The Wigner size choice of the unit cell would be this one. Okay, so this hexagon here would be the Wigner size choice of the unit cell. If I repeat this unit cell, if I translate it by, you see, by, for example, this lattice vector, I'm going to generate this hexagon. If I translate it by this lattice vector, I'm going to generate the hexagon here. So I'm going to fill the whole space without overlaps using this hexagonal tile. Good. Well, determining the area of this object is not straightforward. You can do it, but it's not straightforward. If you wish, we can do it. The simplest way to do it, oh, by the way, we need the length here. So I said that the A is the length of one of its primitive vectors. So let's take this one here. So this is A. A is the distance between 2 points. This is the length of a primitive vector. If you wish, we can determine using the Wigner-Seitz cell. How do we do it? Well, the Wigner-Seitz cell is composed of 6 identical equilateral triangles, of which the height here is A over 2. So the height is A over 2, right? Which means that this distance here, let me call it B. B is A over 2 divided by square root 3, right? If this is A over 2, this is 1 over square root 3 times this thing, right? And therefore, the surface of this triangle of, let's say, 1, let me call it 1, is going to be given by B times H. So A squared over 4, 1 over square root 3. So that's the area of this triangle. And then I simply need to multiply times 6. So the unit cell is going to be given by 6 times A squared over 4, 1 over square root 3, 2. If you wish, you can write it like that. So it's equal to square root 3 over 2 A squared. There was another simpler way to do it, and it was by considering not the Wigner-Seitz cell, but the other cell, the one generated by the primitive vectors. By the way, this is a good exercise to check that these cells must have the same area, because if we are partitioning our space into tiles that for each Bravais lattice point fill the whole space, clearly these two objects must have exactly the same area, right? There's no question about it. So the area of the unit cell is independent of the choice of the primitive vector, of the choice of the way we describe the unit cell, obviously. So it's a good test, to calculate it also for this yellow unit cell and check that the number is the same. But here the calculation is actually simpler, right? Because this is A, and what is the height of this thing? This is 60 degrees, right? So this is essentially, these are two halves, two equilateral triangles of side A, right? So it's, if you wish, this H here is square root 3 over 2 A. So the area is H times A. So it's square root 3 over 2 times A squared. All right? So that's exactly this number here again. So we have verified that the two unit cells have exactly the same area, and it's one of the possible choices in the sheet here. So that was number 5. Any question about this? No question. Yes?
You should solve this now.
Sorry?
How many minutes?
You should what?
If you want to use the calculation
Yes.
on 10 minutes, I'm asking.
Well, I'm, this is, 5th grade, 6th grade, 7th grade perhaps. All right, these are calculations that my son, he's in 10th grade, would do. He would do it in 10 minutes, okay? But you're supposed to do it in 2 minutes. All right, find the area of an equilateral triangle. It's you have to. This is the kind of things that you have to be. You have to do it in 10 seconds. If it takes longer, well, you have to start thinking at your background in mathematics, right? Go back to primary school, perhaps. You know. Yes?
Is the Wiener sites cell defined for non-Bravais lattice?
The Wigner site cell, sorry, say it again.
Yeah, Wiener sites cell.
Yes, so this one here.
Yeah, is it defined for non-Bravais lattice?
Okay, the question is whether Wigner site cell is defined for non-Bravais lattices. We've discussed Bravais lattices and Bravais lattices with the basis, so crystal structures. The Wigner site cell, actually the concept of a unit cell, is equally valid for crystal structures, for Bravais lattices with a basis, as long as you define the unit cell as the one generated by the Bravais lattice that generates the crystal structure. We discussed it last time briefly. So if I had, say, the honeycomb lattice, for example, the honeycomb lattice would be composed of a triangular lattice plus a basis, but the unit cell would be given by the unit cell of the triangular lattice that generates the crystal structure, which means that inside a unit cell there will be 2 points, 2 lattice points, because each Bravais lattice point will have 2 points in the basis. Okay, so each unit cell will contain will contain a number of points equal to the number of points in the basis of the crystal structure. Mind you, some of them might be at the edges of the unit cell. I think that's an important concept, so let me take this opportunity, since you asked the question, to I'll do it here. I think the honeycomb lattice is a very good example of so let me construct the triangular lattice. Well, let me construct the honeycomb lattice, right? So I will do it by first constructing the triangular lattice. So I'm now discussing the honeycomb lattice. And I'm discussing the unit cell of the honeycomb lattice. So I'm now drawing the extra points with yellow color. Right? Now I'm drawing also the lines as guide to the eye. Okay, so this is a possible choice of the primitive vectors. There are 2 points in the basis, this one and this one. So depending on the choice of the unit cell, suppose we choose the unit cell, this one, right? So the unit cell is defined by the Bravais lattice. There are 2 points in the lattice, this one and this one. So you see that each unit cell contains 2 points. When I say this, however, I'm not considering these extra points because I need to choose. If I say that this point belongs to this unit cell, clearly this one will belong to the next one, and this one will belong to the next one, and this one will belong to the next unit cell. So I have to decide where to place it. I could say the 2 points in my unit cell are this and this. Well, then clearly this point will belong to the unit cell here, and so on and so forth. So once I decide which points I want to assign to a given unit cell, I need to make sure that I choose the right ones, or I choose the ones, the correct number of them. Here, for example, a natural choice would be to say that this and this and this belong to the unit cell. I'm not placing this in the unit cell because this one will belong to the next unit cell, obviously. So there are 2 points in the unit cell dependent. But I have to be careful because in some cases, they might be at the edges of my unit cell, so I have to make sure that I assign it to the right unit cell. In fact, the problem would be even more complicated for the Wigner sites choice of because if I take the Wigner sites choice, the Wigner sites choice is something that looks like that. Yeah. So the Wigner-Seitz unit cell looks like this. Remember, I have to choose the unit cell for the underlying Bravais lattice, so the triangular Bravais lattice. So this is the red area here is the unit cell, the Wigner-Seitz unit cell for the triangular lattice of the Bravais lattice that underlies the honeycomb lattice. Now here the problem is even more serious because I have certainly one point inside the unit cell, but then you see I have three points, so it's a bit confusing. I need to make sure that I assign, say, for example, this one only, and if I assign this one to this unit cell, then this one, of course, will belong to the next unit cell. This one will belong to the next unit cell, and so on and so forth. Okay. Another possible choice, I mean, you can say also that I assign a fraction of this point to this unit cell, say 1/3 of this point, 1/3 of this point, 1/3 of this point. So just assign the fraction that belongs, if you assume that these are circles, you can assign fractions. This is an easy way to make sure that you count the atoms, the points properly. So you have 1 plus 1/3 plus 1/3 plus 1/3 makes 2. Okay? So this way you won't be wrong. Of course, you have to work with the fractional points here, so it's a bit complicated. All right. Any other question? Yes?
When we drew this Wigner-Seitz cell, isn't it at the half between the two?
So the question is, when we draw the Wigner-Seitz cell, should the edges go halfway? You have to be careful. The Wigner-Seitz cell is the unit cell of the triangular lattice that generates the honeycomb lattice. So you have to forget about the yellow points. The yellow points are points in the basis. But what defines, before we introduce the basis, what defines the honeycomb lattice is the Bravais lattice of the white points. Okay? So when I construct a unit cell, I have to do it based on the triangular lattice composed by the white points, because that's the Bravais lattice. So that's a very important point that you have to keep in mind. When I discuss a crystal structure, the unit cell is defined in terms of the Bravais lattice that generates the crystal structure. Then after that, you add your basis points on top of your unit cell. That's why you have 2 points in this particular case in the unit cell. If you were trying to construct a unit cell using all points, then you will probably end up with a single point in every unit cell, which is not correct. The unit cell must contain a number of points equal to the number of points in the basis.
So the Wigner-Seitz cell is defined for the underlying Bravais lattice?
Yes, yes, yes. All right. So I have one more concept to introduce for the lattices, and then we move on to the reciprocal lattice. Yep.
What is the difference between unit cell and primitive cell? I mean, I saw unit cell, primitive cell.
Okay. Yes, I didn't want to discuss it, but if you wish, we can quickly say something about it. Now, the distinction. So he's asking about the distinction between primitive cell and conventional cell. You might have heard in the literature that people use these two different definitions. Okay, so we're discussing. Yeah. Primitive cell and conventional cell. Now, you remember the discussion we made the last time about the BCC Bravais lattice in 3 dimensions, right? So we have a cube, and then we place an extra point in the middle of the cube. And we discussed that this can be seen both as a cubic lattice, simple cubic lattice with a basis composed of 2 points, as well as a Bravais lattice by itself without need to introduce basis points. Okay? Of course, the choice of the primitive vectors would be different. In the case of the simple cubic with the basis, the primitive vectors would be the simple cubic primitive vectors. In the case of the Bravais lattice, where you include this point in the Bravais lattice, then the primitive vectors are a bit more, I mean, we drew them. These are the three vectors that identify the primitive vectors for the BCC, seen as a Bravais lattice, not as a simple cubic lattice with the basis. All right, so the distinction between primitive cell and conventional cell is that by primitive cell, you denote the unit cell, in this particular case, of the smallest possible Bravais lattice. That is the Bravais lattice that you construct using these three vectors. It's the smallest possible cell that you can construct out of a lattice. However, last time we said, well, you might find it more convenient to work, instead of working with the Bravais lattice identified by these three vectors, to work with a convention in which you define this as a lattice with a basis, simple cubic with a basis of 2 points. The conventional cell in this case is the cube. So it's it's the unit cell of the Bravais lattice seen as a Bravais lattice with a basis, as a crystal structure, that is, as a lattice with a basis. So the conventional cell here would be the cube. So it would have, for example, a volume equals to A cube. If A is the side of if this is A, of course. While the choice, this one, well, the primitive cell for the BCC is a very awkward object. For example, if you choose the unit cell generated by these three vectors, it's going to be it's a very complicated object. Don't ask me to draw it. I mean, it's a very complicated object. And the volume is going to be how much? Over 2, right? Because the volume of the Bravais lattice is going to be 1/2. We're going to have 2 points in the conventional cell, so the volume of the cell that comprises only 1 point is going to be 1/2 of the, without even the need to calculate it. We know it's going to be 1/2 of the cube. All right, so by primitive cell, you mean the smallest one, and by conventional, you mean whatever makes your life easier if you want to work with the Bravais lattice with the basis. That's why it's called conventional, because it's not just out of convention. You may decide to use. Similarly for the FCC. For the FCC, as we discussed last time, FCC can be seen both as a lattice with a basis, a simple cubic lattice with 4 points in the basis, or as a Bravais lattice with a real Bravais lattice without basis. And the conventional cell in that case would be, again, A cube, if A is the side of the thing. And the primitive cell in the case of the FCC would be A cube over 4, because there are 4 points in the unit cell. So if you assume that each one is a point of a Bravais lattice, then, of course, you have to divide the unit cell by 4. And the shape of the unit cell is actually quite complicated. Yes? Yep.
Because with the primitive cell, you cannot always construct the symmetry.
Correct. Let me repeat it. So the importance of working with a conventional cell is the symmetry, because with a primitive cell, sometimes it's difficult to realize that there is a symmetry underlying. Yes. Correct. Yep. Yes. So the last concept I wanted to introduce, actually there are two concepts I wanted to introduce. The first one is about packing. And in particular, I'd like to define the so-called packing fraction of a crystal. What is a packing fraction? The packing fraction, let me just start by an example. Suppose I start again from my usual square lattice. Okay. Now, the packing fraction is defined as follows. Let me replace, for each point, a circle. So let me assume that I'm filling this space with real objects, balls or circles or something, in such a way that their surfaces touch. So in the case of the square lattice, what I would do is the following, of course. Right? So I'm now constructing a set of circles, replacing points by circles, and I assume and actually impose that these circles are such that they just touch without overlaps. Without overlaps. They can only touch, but they don't have to overlap. So just having, say, balls and decide the radius in such a way that they are completely, there's no other way to make the radius bigger, otherwise I'd start having some overlaps. So by packing fraction, I define the area covered by the spheres, by the circles, with respect to the overall area of my system. Okay? So it's a measure of how efficient I can pack circles or spheres in 3 dimensions in the plane for a given lattice. Now, how do I calculate it? Well, I have to somehow divide the space in some way. The most natural way to calculate this is to say, well, here I have, for each Bravais lattice point, I have one circle. Okay? So the overall area per Bravais lattice point covered by the circles, if this is A, so A is the distance between points. The radius will be A over 2. Okay, so the surface of the circle is going to be pi A over 2 squared, right? That's the area of the yellow region here. So every Bravais lattice point will contribute to the total area of the spheres with this contribution. What about the total space available for each Bravais lattice point? That is given by the surface of the unit cell, right? So the surface of the unit cell here is A squared, correct. That's A. Sorry? The unit cell. We're talking about the unit cell. Oh, that's the area of the whole system, but that's not the unit cell. The unit cell is A. Okay. So I'm now counting. You have to be careful because I have to somehow find the fraction for an infinite system. Okay. So in principle, this is a ratio between infinities. The infinitely large area occupied by all the circles, which is infinity, of course, for an infinite crystal, and the infinitely large area covered by the whole space, which is infinite. So I have to, when I take this fraction, I need to be careful. I need to do it per, for example, per Bravais lattice point. I take a single Bravais lattice point and I say, each Bravais lattice point I will have a contribution from the circle and the contribution from the overall space that the single Bravais lattice point contributes to the whole space available. So the area occupied by the circle is this. The area occupied by the unit cell is this. Obviously, hopefully, this number is larger than this one, right? Because otherwise, I did a mistake somewhere. That is, the area occupied by the circles must be clearly smaller than the area occupied by the unit cell. So by packing fraction, F, I define the ratio between and this is pi over 4, which is reasonable. We like it because it's less than 1. If it was bigger than 1, there would be a mistake, right? Because we know that there must be empty spaces. It's also reasonably close to 1, right? We know that these circles are going to occupy most of the space, so it's certainly going to be more than 1/2. In fact, pi over 4 is how much? 0.74 or something like that, right? Roughly. So we're talking about something close to no, more than that. Sorry, 0.76. Does anybody have a calculator? Right. 785. Can anybody give me the number? Oh, you did it already. Okay, fine. Correct? Fine. So that is roughly 78 of the space is going to be occupied by the spheres, and the remaining 22% of the space is going to be left empty. Is there a better way to pack circles in 2 dimensions? Yes, we discussed it last time. What is it? Triangular lattice. So let's recalculate the packing fraction for the triangular lattice. Yep, let me.
When we calculate the area, we take the unit cell, right?
Of course, yes.
If we consider lattice with a basis.
Wait a second, I'm coming. So this is, sorry, yes.
When we consider lattice with a basis, which one should we choose, the unit cell or?
I'll come back to in a minute. So let's calculate it for a triangular lattice. All right, so right? Now, clearly, I'm leaving less empty space, right, if I do with the triangular packing. But how much? Well, if this is A, the area of the circle is the same, right? Pi A over 2 squared. What about the unit cell now? That is the area per of the whole space per Bravais lattice point. We calculated already, right? So it's square root 3 over 2a squared. Packing fraction, pi over 4 divided by the area of the unit cell, 2 over square root 3, right? A square, of course, is 2, 1. So it's pi over 2 square root 3. Calculators?
I think if we square, if we take y to be 3, and then if
Very good, but I mean, it's quicker if we... Let's believe in calculators once in a lifetime. 9? No, it's too much. 9? 0.90? Correct? Wow. So it's 91%. Right? So we have definitely improved over 78% of the square lattice. We're getting very close to 1. We'll never be able to get to 1, obviously, right? There's no way in which you can pack spheres or circles and fill the whole space. So that's the best we can do in 2 dimensions, 0.9, I mean, 91% roughly. So we leave behind only 9% of the space if we pack objects like that. By the way, I mean, this is a trivial exercise, but it's something that companies doing packaging care a lot, of course, because if you're able to minimize the volume of your of the goods that you are shipping, it's real money, right? So that's why, I mean, no wonder that they're now with these new packagings, they are preparing these boxes, hexagonal boxes, because you can gain also this 9% left if you use an hexagonal box. Well, a square box, of course, will be even better. All right, so let me extend this concept, however, to 3 dimensions, because 2 dimensions is easy, 3 dimensions is a bit more complicated. Up. Yep. Exactly. It's a purely geometrical exercise. And the reason why we're doing that, thanks for the question, is that if in the assumption that atoms are spherical objects, that gives us a very nice geometrical prescription for the best way in which we can pack atoms in a crystal. So no wonder that the number of crystals well, in 2 dimensions, it's not relevant, but in 3 dimensions, we will find out, actually, we will not, but you can find it in textbooks, that the FCC structure is the one that packs the spheres more efficiently. Together with HVP, they have the same packing. So no wonder that the number of crystals take the FCC or the HCP as their crystal structure. It's because atoms are spheres, and atoms like to get together, and the best way they can get together is by forming the closest possible packing of spheres. Oh, yeah, you can see it that way as well, yes. Although then you find crystal structures, even elemental crystal structures, which are tetragonal, and you say, is that the proof that atoms are not spherical then? Well, not really. It's different.
The inside of the atom, I mean, the configuration of the charges, I don't know, because then you will have something which is not spherical.
I mean, if you know a little bit of chemistry, and you certainly know chemistry, you probably know that the atoms that come closer to a spherical unperturbed configurations are the rare gases. All the other elements, you bring them close to another atom, they will start doing chemistry. So you start losing this nice spherical appearance, and that's why not all the atoms form close packed structures. They like to form more complex structures. But there is a category of elements, the rare gases, the noble gases, the right-hand side of the periodic table, which are very inert. They don't like to form any chemical bond, and they remain spheres. Unfortunately, these atoms are also, I mean, the fact that they don't like to get together means that it's very difficult to form crystals made out of only of noble gases. It takes a very, very low temperature. In fact, in the case of helium, there's no way you can crystallize it. Helium is the first one, right, of the noble gases. That's because of quantum effects. It's a different way. But even if, say, you were working with helium at the classical level, helium would probably crystallize at temperatures of below certainly 1 Kelvin. Okay? And the other noble gases, you can crystallize them, but we're talking about temperatures which are very, very low. So it's very difficult because their interaction is weak. So But when they form crystals, they typically form FCC or HCP crystals because they're really spheres. I mean, their electronic charge never gets perturbed by the nearest neighbor, so they remain spheres and they pack like a close-packed object, FCC or HCP.
Okay, another question.
Yep.
If it's possible, if we can make the packing fraction to be 1, I mean, if we can make.
Yes.
Okay, and then which is good. Which is important.
What do you mean, which is important?
Is it important to
So the question is, sorry, if you can make the packing fraction 1, which is impossible,
but okay.
what would you learn out of this?
Yeah.
Well, you would learn that there is some structure that allows you to pack atoms, spheres very efficiently. So the question would be, why don't we see it in nature? Right? That would be an interesting question. Obviously, the answer to the question is that there are no crystal structures with packing fraction of 1, of course.
Okay, then, is it important to have a space like?
Oh, it's interesting. I think it's interesting. It's important about what?
Is it important, okay, or is it nice to have like a packing fraction which is not?
Yes. So the question is whether it's interesting to have a packing fraction which is not close to, I mean, well, not the largest. Well, the answer is yes, because then you learn about different ways in which atoms can pack. The reason why they pack in that way is not because they are spheres. So then you learn that those atoms are not going to be approximated by spheres. If you find a very low packing fraction for a crystal, then you can say, well, these atoms are not going to behave like spheres. They're going to behave like objects which form one-dimensional structures, more complex structures. So it's a very simple geometrical concept. Yes?
Okay, I want to know just the importance for packing.
Yes.
How you can do it.
What do you mean, how we can do it? How we can calculate it, or?
Not calculate. Okay,
how?
You know it already, or you should.
You know it always, or you should.
Let me.
Yep.
Try to find out. Okay, I want to know. You say packing fraction, okay? So maybe you want to pack some atom.
Yes. I want to pack some atoms. Yes.
Okay. You know it, or just by the calculation,
Let me try and explain it a different way. So, it's not that we design materials and we say, okay, this triangular structure is the one with the largest packing fraction, so let's make a material that looks like this. This is not the idea. This is not the reason why we do these calculations. We do these calculations because we know that there are materials that pack in this way, and we want to understand why they do it. And the reason why they do it is because we realize that in this way we optimize their packing. So we can manage to bring the atoms as close as possible to one another in a macroscopic way. We leave no empty space or very little empty space by doing this.
So you can have some packing fraction and then you can change if you want maybe to change.
It's not, there's no way we can change the crystal structure of a material, with exception of perhaps applying temperature or pressure or squeezing your crystal. Then you can induce phase transitions if you wish. There are systems that say at ambient conditions, for example, take the cubic structure, the square structure, and then you compress them, and eventually they transform into more close-packed crystal structures. It is a very simple and qualitative way to understand why FCC, HCP, close-packed structures are so common in nature. Why are they so common? Here it is, because it's a very efficient way to pack spheres. Okay, and measured through this geometrical number factor that we've identified. Yes?
So from can we use this method? Because in universe,
Yep.
there are some objects
Yes?
you can consider as like solid. Like, okay, in macroscopic scale.
Okay, so there are objects that look like solid at macroscopic scale. So you're talking about a planet is made of matter,
No.
and it's made of crystals. No.
Oh, yes.
Or you're talking about the arrangement of planets in the...
Can we
You mean this is a planet and this is another planet? Is this what you're trying to say? Well, clearly you cannot, because there is no interaction, physical interaction, with the exception of the gravitational force between planets. So I don't think this concept, I mean, if you look at matter at the end, say at the scale of the universe, particles, atoms, planets are never that close to justify this treatment. You really need the things to be touching in order to apply these statements. So I doubt you can say that the moon is close packed to the Earth or something like that, right? They need to be touching in order. Not only, but you need to have objects of the same size. If I start playing with objects with a different size, well, you're lost. I mean, there's no way you can come up with...
We have some other atom in the lattice.
Yes?
Which has not the same size with...
Okay, so that's a different question. You're saying you can have different atoms in the lattice, but the atoms can have different sizes. But you're talking about a crystal with atoms.
Even the crystal.
Yeah, you can have different atoms, right? Yes, of different sizes. But, I mean, an obvious example is say, a binary system, a crystal made of two atoms, a big one and a small one. What is the best way to pack an object made of an equal number of big spheres and small spheres? Even in 2 dimensions. That's tricky because, well, if you, for example, if the radius of this is small enough, then you can place in the middle. But then you have a square lattice, right, with the bases here and here. If this has a size which is very similar to this one, this packing is no longer correct, or no longer the best one. This one becomes better, right? Actually, in the limit that this is equal to this one, we know that this is the best way of packing circles. So depending on the ratio between the radius of the two particles, you may have different best ways to pack them in a binary crystal. So the concept of packing in a binary system is much more complicated than the concept of packing for a Bravais lattice, okay, where you only have one sphere, one type of sphere. So what we're doing is a very simple theory here. We're not considering more complex configurations, more complex geometries. For example, a binary system.
So should be considered as crystal only structure where the atoms touch each other.
No. So the question is whether we consider crystal only a system in which the atoms touch. I guess I start to understand what you probably mean. You want to know whether you can treat with the same formalism, mathematical formalisms, systems that are not, strictly speaking, atoms, crystals made of atoms closely spaced, atomic distances. You want to study something more macroscopic particles. Okay, you can, but your macroscopic particles must have important properties like being always, the same size. Atoms, you're guaranteed, right? If you have aluminum, you're guaranteed that all the atoms will have exactly the same size. 10 to the 23rd atoms, all with the same size. So you can play these games very easily. Now you can synthesize particles, spheres. Well, take soccer balls. Yes, you can agree. You take soccer balls, they all have the same size, and you can pack them. And in fact, these concepts, are equally valid for packings of soccer balls. Not that this is particularly interesting from a practical point of view, right? But your objects must be identical in size. If they're all different in size, well, there are probably theories that describe packing of particles of random sizes, but they're probably going to be very complicated and depending on the system you want to study. Yeah, last question, because otherwise we'll...
Then looking at the previous question.
This one? Yep.
If we look at it as maybe you having a certain size.
Yes.
Then you have maybe others which are smaller and you go on feeding in.
Oh, you mean here?
So comes back. Yeah, okay. For example, if we have only one.
Right.
If it keeps keeps on growing, we realize it will come to this
Right.
default.
So that's, yes.
So
Let me repeat it because the microphone. So what you're saying is that if the particle is small, it can fit inside the empty spaces of this square lattice. But when it grows, it will eventually have to become like this. This is what we also said before. Yes. Then?
So we can, for example, if say it was a company, maybe it is packing, maybe they are pricing according to the way it is.
Yes.
So they can say maybe if you buy this commodity and we pack it together with this, maybe the pricing is this. If you do this, maybe.
Yes. I'm afraid we're moving a bit too far out of solid-state physics. Yes. Very last question.
I'm really interested okay. The packing fraction not being greater than 1 tells that there is an empty space, right?
Yes. So the packing fraction being smaller than 1 implies that there must be empty spaces. Yes.
And then is it really empty, the space? Okay.
Well, okay, the question is whether this space is really empty or not. If we deal with spheres, of course it is empty. Real system is made of atoms, and atoms have a density which decays exponentially with distance from the center. So the answer is no, this will never be empty. But there will be a point at which two atoms essentially are not impenetrable. So they just stop because there's no way you can push them further. All right? So this is not empty space. This is not just the only field space. It's a charge density. Right? So again, this is really just a geometrical theory that perhaps mimics the truth, but is certainly not not really the truth. The truth is that, as you say, atoms have charge densities, and there is a peak in the charge density here. There is a tail, and this is not really empty, and there's no, say, fixed line that we can, no border where we can say the density drops to 0. Of course, the density will be a continuous function of the space, and so yes.
So, then it's not important to talk about packing fraction because for each thing, that thing is there to those.
No, okay. So the argument is that, well, why do we talk about packing? Because these are not spheres. The atoms are not spheres. They are smooth objects. Okay. Well, the answer to this is that it is true that atoms are smooth objects because the density doesn't go to 0 abruptly. But it is true that when you bring together two atoms, there is a point at which they find their equilibrium. Okay. So you can say, okay, atoms like to stay at a distance a from one another. Now, whether you put the boundary or not, it's irrelevant. As long as you say two atoms like to be at a distance a and they are spherical. This one likes to be at a distance a with this one, distance a with this one, distance a with this one. Okay? That's equivalent to saying that there is a hard wall that keeps the atoms far apart from one another at distance a over 2, at the radius of a over 2. Okay? So it's equivalent.
So it's just like to study the structure, but not, I don't know.
Again, it's a very, we were supposed to spend 10 minutes on this. We spent way more on this. So it's not really a central topic in solid-state physics, but it is something that I think is important to realize because I think the take-home message is that I hope it is clear by now that these kind of structures pack atoms more efficiently than this one, the square one, and therefore you should expect to see more frequently these kind of structures than these ones, period. Very qualitative.
No, not question. Just about the we can continue.
Sorry, which?
We can continue.
Yeah. No, we're going to go until 45 at least. So, okay. All right. Now we're going to move to 3 dimensions. So put on your 3D glasses and black and white or blue and red. Sorry, I forgot to. You asked me. Some of you asked me about the crystal structure. How do I define a packing fraction of of a crystal structure of a lattice with a basis. It's the same, right? So suppose I introduce again the honeycomb lattice, our usual example of a crystal structure in 2 dimensions at least. All right, so I have to build here circles. Now, of course, I need to assign to every point a sphere, because I want to mimic the presence of atoms here at the lattice points, right? So this is the best way in which I can have spheres packed in the honeycomb lattice. They touch and they don't overlap. How do I evaluate the ratio between the filled spaces and the empty spaces? Well, you clearly see that the honeycomb lattice is not particularly good as a way to pack spheres, okay? In fact, the only example, as we discussed last time, of a honeycomb lattice in nature is the carbon, graphene, the single graphite sheet. Now, carbon happens to be an atom which forms a covalent bond, very strong covalent bond. So the density around a single carbon atom, when it starts forming bonds, is certainly not spherical. Okay? So this is not a good approximation to the, but still, I mean, it's a good concept to study. So we will have to find out something which is not too big, because if it's too close to 90%, there is something wrong with this. How do we calculate it? Well, we need to, again, to find the, we assume that this is A, our usual length, A. So the radius, the area of the circle is our usual pi A over 2. How do we compare it with the empty, I mean, the overall space available? We have to be careful now, because previously we chose the unit cell. The unit cell is a good choice, and let me draw here a unit cell, one of the many possible unit cells, this one here, right? Notice that I'm using the Bravais lattice here to define the unit cell, okay? That means I have 2 points in the unit cell, because it's a honeycomb lattice, it's not a Bravais lattice, it is a crystal structure, so I have a unit cell that comprises 2 points. But then I have to be careful, because if I now define the area of the unit cell, I have to be careful about 2 things. First, that the side of the unit cell is not A. What is it? A times, yeah, square root 3. Was it the one? Okay. So this length here is A square root 3. Why is it? Well, you see it here, right? This is A, this is 120 degrees, so this is A square root 3. So A square root 3. So what is the area of the unit cell? It's squared square root 3 over 2, right? It's the side of the unit cell squared times square root 3 over 2. We already determined that. Fine. So we found the area of the yellow unit cell here. But now we have to be careful, because for every unit cell, we have 2 circles that belong to that unit cell. Okay, so when I'm going to evaluate the space occupied by the circles, by the spheres, versus the space, the overall space available, for each Bravais lattice point, to which I assign the volume of the unit cell, as the volume, the area available, the full space available, I need to remember that for each Bravais lattice point, I have 2 spheres, 2 atoms, 2 points, right? So when I do my comparison in terms of packing fraction, I have to do twice the area of the circle divided by the area of the unit cell, right? Is that clear to everyone? No? Okay. I need to evaluate the ratio between the area occupied by the circles and the overall area of my available in my system. So let me partition the space per Bravais lattice point. I'm going to evaluate the total area covered by the circles for every Bravais lattice point, and I'm going to take the ratio of this value with the area, the total area available per Bravais lattice point. I need to do it per Bravais lattice point because if I took the whole system, there would be the ratio between two infinities. So I need to restrict myself and say, okay, let me take every Bravais lattice point, and for every Bravais lattice point, I count how many, what is the space covered by the circles, and what is the space total space available per Bravais lattice point. Now, the answer to the second question is easy. If I want to know the area available per Bravais lattice point, that's the area of the unit cell. Yellow. Remember, here this is a crystal structure, so the Bravais lattice is underlying, and it's this triangular lattice here. That's the area of the unit cell. However, every Bravais lattice point has now two spheres belonging to each Bravais lattice point, right? There is twice the number of spheres with respect to the number of Bravais lattice points, because this is a lattice with a basis, with 2 points in the basis. So there are 2 spheres per Bravais lattice point. Okay, for every yellow point, there are 2 spheres, right? I'm always leaving behind 1 white point. So for every Bravais lattice point, I need to count 2 spheres, because it's a lattice with a basis, with 2 points. So every Bravais lattice point will correspond to 2 spheres in terms of volume occupied by the spheres. Right? So I need to place a 2 here. When I take the overall ratio between filled space and space available, I need to consider that for every unit cell, I need to place 2 circles. Sorry, this is a square, of course. All right, so we have 2 pi a squared over 4 divided by a squared 3 square root 3 over 2. Pi over 3 square root 3 0.64? Yeah, which is very bad, of course. Now, there was another way in which you could have calculated it much quicker than that. If you take a look at this picture, what if I place an additional circle here? What do I obtain? The triangular lattice, right? A triangular lattice of spheres. So what am I doing here? Out of a triangular lattice, I'm removing 1 sphere out of come on, 7, 6, how many? 6? I'm removing 1 out of 6, are you sure? 3? Out of 2? Come on, it's 2, 3, 6, 7, or what? Shall we vote? If I remove the red ones out of a triangular lattice, how many spheres am I removing on average? I'm removing 1 out of?
1, 4, 5.
Come on, that's geometry. Let me do this. Oops. Do this. So I have groups of 3 spheres, and I'm removing 1 out of 3. Okay? You see? You see it now? You have these 3 objects, 3 objects. You're going to have 3 objects here. Well, we will have to multiply, but anyways, there will be a red one here, so you will be removing these 3. So you're removing 1 out of originally 3. So the packing fraction of the honeycomb lattice compared to the packing fraction of a triangular lattice is 1/3, 2/3. Here you go. Was 906, right? The other one. Okay? Good. So we got something, I mean, not so nice. 0.6 is really poor for a 2-dimensional system. 3 dimensions, even more complicated now. Okay, packing fraction of a simple cubic structure, simple cubic crystal. All right. I have to be careful that I'm in 3 dimensions now. So I have spheres, real spheres, in 3 dimensions. I'm not very good at drawing this, but okay. So we're going to have a sphere that is going through here, here, here. Right, so it's touching this point, and this point, and so on and so forth, right? The important thing is that this sphere is touching the other sphere in the center of the connecting line, right? And these are also touching here. Okay, so now it's no longer surfaces that we're talking about, but it's volumes. We're in 3 dimensions. So this is A, the distance is A, so this is A over 2. So now the volume of the sphere (4/3 pi A over 2 cube, right? That's the volume of one sphere. What's the total volume available per Bravais lattice point? It's the volume of the unit cell. Volume of the unit cell? A cube. Great. Packing fraction? 4 pi 3 times 8. In fact, 2 pi over 6. 50%. 5? 2. 2, 4? 52%. You were hoping for more, right? It's only 50%. So if you pack spheres in a cubic lattice, you're going to waste 48% of almost the same. You're leaving empty almost the same amount of space you're filling with spheres. Anything better? Let's do the, what would you like to do, BCC or FCC? FCC. You want to go the hard way. Let's do the FCC. Actually, we know that this is the best one, right? So let's go directly to the best one. All right, so an atom is here, another atom is here, another is here, 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 here. There's another one in the center of the face, center of this face here. But don't ask me to draw more because otherwise it's, Now I have plenty of balls around me, okay? Suppose I sit here. Now the crucial thing for me to decide is what is going to be the radius of my sphere, right? That's really the most important element in our discussion. How far can I move with my ball before I start touching some other balls? So what I need to find out is what is the neighbor, the nearest atom or point to myself, right? Because this is going to be the limiting radius. I need to find out among the infinitely many Bravais lattice points which one is the closest to me, because he will also have to create a sphere and the two of us are going to touch. So I need to identify the point that is closest to me. Is this the closest point to myself or not? If I'm here, is this the closest point to myself? No. This one? Right, correct. So then this is the connection between these 2 points. I don't even need to draw any circle, any sphere here. I know that the radius of the sphere must be 1/2 of this connection, right? So if this is A, this length is A over square root 2, and this is 1/2 of it, right? So the radius is A over 2 square root 2. Volume of the sphere, 4 pi over 3 A over 2 square root 2 cube. Unit cell? A cube? Over 4, correct. For every sphere, I mean, there are 4 spheres in the conventional cell, in the cube, right? So I need to divide by 4. I need to take the primitive cell in our definitions. So then ratio, 4 pi over 3, 1 over 8 times 2 square root 2 divided by this, so times 4. This go away. So it's pi over 3 square root 2. We've done a much better job, but we're still at 74%. Right? There's no better way to pack spheres in 3 dimensions. And if we pack spheres in the closest possible way, we leave 26% of empty space in doing that. No way. I leave you as a homework to calculate the packing fraction for BCC. All right? So, homework. I'm not going to grade it, okay? But please do it and we'll discuss it on Wednesday. Calculate F for BCC. Hopefully, it will lie somewhere in between this number and that number. If not, There would be something wrong in your calculation. Yes, I think we better stop here because there is the next concept will take me at least 10 minutes, 10, 15 minutes. Okay, so we stop here. I hope there are no more questions. We had several. Okay, last question.
How do we define it in one dimension?
How to
Define it
in one dimension? You want to define the packing fraction in one dimension. That's a very good question. Let me ask the question to you, to all of you. What is the packing fraction of a one-dimensional crystal? Actually, of a one-dimensional Bravais lattice, sorry, to start with. One. Why not? It's one. If you have a one-dimensional crystal, right? What else? I mean, well, you don't have spheres, but you're going to, I mean, it's easy. You can just pack segments, and you can do it with packing fraction 1. A Bravais lattice. If you have a lattice with a basis, that is, if you have 2 points, then, of course, you're limited by the distance between the 2 points, right? You have to consider segments that are, so that depends on the ratio between the distances, of course. Yeah, it's a good point, yes.
A sphere in a 1D is just length, so.
Yeah, whatever is it's a set of points that have the same distance from the point yourself. So it's only 2 points. Sorry?
In higher dimension, it would be like the hypersphere.
Of course, yes, yes. We're not going to discuss packing functions in 4 dimensions. But. All right, so I'll see you on Wednesday.